Hi, welcome to Innovation Briefs. My name is Rich Freeman with Freetech Plastics, and today we're going to talk about thermoforming with style. And what do we mean by that? Well, thermoforming is a process that is used very widely. It's one of the largest users of material by weight. And for example, industrial equipment uses the thermoforming process, as well as, I wonder if there's another way to do this, as well as the food industry. For example, almost all those yogurt cups, sour cream tubs, all of that stuff is all thermoformed on form, fill, and seal lines, and that's where you see pretty much the largest use of this material by weight. Also, that annoying packaging that you have to use a buck knife and 3 pairs of scissors to get into is generally thermoformed, and that's all for to help the anti-pilfering industry. I don't like it either. I wish my brethren in the thin gauge would stop it, but it's really driven by customer demand and by the pilferage issues. So it can be used for all sorts of packaging, both food and other things, and in fact a lot of clean room materials, a lot of surgical instruments that get passed across a sterile field will come out of one package. The inside package will come and be passed across a sterile field. A lot of your signage, almost all the big signs that you see everywhere are thermoformed acrylic. Quite often they're back painted and they're distortion printed, and then when they format, the letters and everything pull into the proper shape. Thermoforming is also used very widely in the marine industry. This particular sailboat is actually thermoformed out of 2 pieces. They put a layer of foam and composite in the middle of it, and then they press it all together, and it's essentially a single contiguous unit. The heavy gauge truck industry uses a whole lot of thermoforming, from bumper surrounds to interior cab parts to fender skirts. And what they found is this bumper doesn't have it, but they split the bumper at the very corner there, and they'll use a thermoformed chrome plated plastic bumper that when they hit something it gives and breaks, and they don't have to replace a $1,000 bumper, they replace a $300 or $400 part. Medical equipment is another area where thermoforming has been used, especially pressure forming in many aspects. This is ultrasonic a piece of test equipment. This is a surgical laser. This is one of the original surgical lasers, and it was used for both cosmetic and for general surgery. And the reason they chose pressure forming is for lightweight, and we'll talk a little more about this part as we go on, but it had some interesting challenges. This is an electronics unit. This is something that will turn a 4-color photocopier into a 4-color printing press, do all the color steps and everything. We see printing and photocopying merging closer and closer together, and this is one of the first machines that was doing that. But you can see that we can get some very close detail on the parts here. Not something you typically associate with thermoforming. So what are thermoforming's advantages? Why should we thermoform things in the first place? Well, first, it's very strong and lightweight, as evidenced, for example, by those packages you can't get open. They're very thin plastic, but they're very strong. They also have low internal stress, so that gives them high impact strength. And they have low or economical tooling costs. So there's a big advantage there too. For example, on the lightweight, if you were to take a rim part, a reaction injection molded part, and hold it next to an identical thermoform part, there'd probably be 25 to 40% weight reduction in the thermoform part, and the impact strength would be nearly double. The economics for tooling are pretty interesting. We've just used a 20 by 40 cavity here for an example. If it was injection molded, you ordered that mold in this country, it'd be about $200,000. If you pressure formed it, it'd be about $10,000 to $25,000, depending upon complexity and slides and that sort of thing, how many undercuts you did. But there's a significant savings, and as the parts get larger, the savings gets bigger. So when you start getting up into parts that are 36 by 48, 48 by 48, 48 by 72, now the cost difference between thermoforming and injection molding becomes really significant. The basic difference between what people call vacuum forming and pressure forming is vacuum forming uses atmospheric pressure. That means the most pressure that you can get on a part at sea level with a perfect vacuum is 14.7 pounds. If we seal it in a pressure vessel and pump 70, 80 pounds in there, now we not only have the 14.7 that we get from atmosphere, now we multiply that by 3 to 5 times. There's some machines, and we have one, that are capable of doing 268 psi, at which point you can pressure form composites. Just another example of the difference in the way that the sheet adheres to the mold. A lot of people use pressure forming in parts that are going to be lower cost, for example, than maybe an injection molded part. And quite often they're used in conjunction with sheet metal. So we ask the question, what can you do with a square box? Well, you could just leave it a square box, and that's called a refrigerator normally, and they don't look very interesting. Or you can dress it up in front with a really nice cover, and that's what Hewlett-Packard chose to do on these particular units. And they were for high-tech video gear. These were the first video online, on-demand servers there ever was, and they were trying to sell these to the phone company, and the phone company had started to buy them. And then the phone companies thought, well, why don't we just buy the cable companies? And that's why you have AT&T Cable today, and they kind of shelved this project. Funny story, NYNEX in New York, a friend of mine happened to be the vice president of technology for this division of HP, and he's in talking about all the whiz-bang servers and electronics and stuff that are in there, and the president of NYNEX turns to him and says, "Al, that's really a nice door." I love that story. This is that surgical laser we were looking at earlier. This was for general, and it was the big use ended up being the facial resculpting. It was the first facial resculpting laser, and they would go in and they could knock, sometimes 20, 30 years off of somebody. I saw some of the videos, and it was amazing. Here we have another basically a square box, and simply by putting a cover on here, took a very inexpensive package and made it a very nice looking part. Ribs can be formed down to 100 thousandths thick, so you can really maximize airflow through a part, and we'll show you a part later where that was very important. Undercuts can be molded. Really, we say pretty much up to an inch, no problem. If you need something more severe than that, then we need to talk about the way it's designed, but generally a 1-inch undercut is not any big deal with a really good quality pressure forming process. Here's the reason for that. Now we've got all these recessed areas, we can hide all the hardware. And the other thing we can do is we can mold features down as far as small as 40 thousandths. Some circumstances we can even mold features as small as 20 thousandths, raised features. And we've got a couple products in the booth that will demonstrate that. Here was the first surgical laser. This is the intuitive Da Vinci surgical laser that actually won grand prize here a few years ago for best medical device, and it won every major design award, and it won every major plastics, thermoforming, and manufacturing award in the country. And the difference, they've changed this quite a bit. At the time, all they had was cathode ray tubes, and they had to stick 2 cathode ray tubes in here to get the stereo vision. And so that's the reason this top cover is so big. If you've seen the newer Da Vinci, the top cover is much, much smaller because now they have some really good flat screens that they can put in there that are really high resolution, and it eliminated the need for a lot of the technology that we put in this part. The surgeon would sit here up to 12 hours. And so another thing that we did is we molded some undercuts along this side, because most people would have just trimmed that and it would have just been a sharp saw cut edge, maybe with some paint and been sanded down. But by putting a nice rounded edge there, when people maybe were in there bumping it, then that way it just didn't add to the aggravation of the doctor trying to work in a pretty delicate situation. And one of the things that we like to do with people, we work with a lot of industrial design firms. We try to get in early on the project, because if we're in early on the project, that helps us in the sense that we can help you with the technology that you need from our aspect to make these little improvements that are really only paid for once in the tool, and it doesn't really matter because the amount of time it takes to trim the part out anyway is going to be the same. This is another example of a square box being dressed up. And this particular unit here was actually, it's actually won an ID Magazine award back in 1989. But really the interesting part about this is the story behind it. When this company came out with this was the first desktop genetic reader. So before, all genetic testing had been done kind of in just gels on a bench in a lab. And these guys were the first guys to basically automate it. And it was a desktop unit. Well, what was interesting was they went out and said, okay, we think we can build a company around selling a bunch of these at $35,000 a year. So they got a few mock-ups of the industrial design and they took it around to laboratories and things like that. And they said, what do you think this thing would be worth? Well, the answer came back $75,000. So they went back, laughing all the way back to the bank, and they said, okay, well, we'll go out at $75,000. That's, you know, that's only $40,000 more than our business model. And they sold a bunch of them. And then when everybody reverse engineered it and came out with the Me Too models, they dropped their price down to 40. They were still above their original business model, and of course they just kicked butt in the marketplace. All because of a plastic cover. This was an interesting challenge. You have a part here that's got a very severe draw, and then you have off at an angle here with all these undercuts that are going to be molded in. But you can see why it was necessary. You had a box that you were trying to separate where the sample goes in. This is a chromatography machine, so here's where you insert the needle for the sample, and they wanted to keep that separate so they didn't show up the screen. So we put this barrier around here and tilted that back, and that way it was easy to read. And even though it was a little bit of a technological challenge to make, it made a really nice product. And again, you took a sheet metal box and you made it very nice looking. This is an interesting example of thermoforming, and I show it because just to give people an idea that you want to think outside the box. This is a product called cavity floor. It's used very widely in Europe and South America. What they do is they thermoform these, and then they lay them out on a floor, second, third, fourth, fifth story in a building, and they fill it with self-leveling cement. And it's called cavity floor. And you pipe your air conditioning in there, you run all your wires in there. Where you want a vent, you just cut a hole and you put a vent in there. And you're really standing on thermoform parts with as little cement concrete as possible. It's a very lightweight solution. And like I say, it's really used a lot it was originated in Germany. It's used a lot in Germany. It's used a lot in South America. Another aspect of thermoforming is twin sheet thermoforming. And this is where you actually take two sheets and two molds, and you bring them together, and you have an air charge in the middle, and you pressure form from the middle out to both sides. And you can also, while the sheets are separate, you can put in, for example, steel inserts and reinforcing. This is an example of a tractor roof. And so the outside is one color, and it's yellow, and the underside is black. And since it's out in the weather, it provides an insulative area because there's a large airspace in there. There's also some metal reinforcement in there in case the tractor rolls over, and then the fasteners are molded in as well. This is an example of a duct. And so anytime you would think of a blow molded part where you didn't have the economics to spend the money to blow mold it, twin sheet thermoforming might be a good solution for you. So this is an air ram for a M3 BMW speed kit. And the material is 15% glass filled nylon, so it can handle over 400 degrees under the hood. And if your BMW M3, which comes out with about 400 horsepower to begin with, isn't fast enough already, you can put this kit in it and it'll give you an extra 10% horsepower. And they put new chips and stuff like that. But the whole purpose of this is get the air into this huge cold box and make sure that the air doesn't bounce down on the air cleaner, because if they get this vortex swirl effect, then they can get more air through that air filter quicker. And you can see how the process works. You're basically just welding it together. You can see the welds there. This is a twin sheet thermoformed chip carrying box. You can see the grooves for carrying the 300 millimeter semiconductor wafers. And this is for transport. This is all hollow. And it's basically formed flat and then all folded up together. So there's, I mean, you start thinking about the things you can do with thermoforming, you know, there's just lots of different avenues that you can take, and really a good creative designer can pretty much make any product. This is a little study of some of the R&D that we've done with people and how we've gone through processes to help people reach and accomplish a design goal. Now, lab equipment's pretty sterile usually, and this is what the unit looked like before we got started with the industrial design people. And it took up, you can see it took up a whole workbench. And the whole idea was to get this into one bay in a lab, because lab space is expensive. And what this is a machine that basically gases mice and then takes pictures of them. And so we kind of joke, they kind of put the mice in there, they gas them, they take their picture, they post it on the internet. It's kind of like the parking lot at a Grateful Dead concert. This is a big camera up here, and they wanted to try and make this thing look a little more refined. So here's what they did. They took the camera and they put it up here and they put it under this translucent dome. And this part's over in our booth. We're over in 1883. There's my commercial plug. This part's in our booth, and you can actually see this, but they put the camera up here, and then this is where they put the mice, and here's the valve that they use to turn on the gas, and then the rest of the electronic equipment is down here for it. And so they condensed this all down into one bay size. They wanted a really nice monolithic look. They didn't want anything sticking out, so we molded in all sorts of undercuts on this so that when they were all done, they just had a super, super clean look. The letters here that you see, those are raised up 1/4 of an inch, and then the actual letter area is molded back down inside so that those are laser cut inlays, and they can sit down in there, and that way you don't snag anything on the edge of them by having them set back in there. Again, just here's another undercut. We were told by our tool maker that this wouldn't work, and they didn't want to finish the tools, so we said, look, just do what we tell you. We'll pay you for the tools whether they work or not. And you know, that's sometimes the argument you have with tool makers, because they don't know what you're doing and you don't want to tell them what you're doing. So we think that the combination of thermoforming and industrial design paid off really well. This is a unit that goes into universities and research labs, and it basically sells about 100 to 150 units a year, and it's a pretty pricey unit, but they made it look pretty good, and then they saved half the space that it took up before. So it's become a very popular unit, used mostly for cancer research. This was, we jokingly refer to this as Spider-Man's server. The individuals, back when Lucent was still part of a standalone company before it got bought, this was a desk side server, and what they normally did is they would normally have these in a rack mount off in a server room somewhere, but every once in a while they needed one out by a desk or remote. And so what they did is they came up with this enclosure. And it's, again, really simple. It's a sheet metal box with a top and a front cover, and they needed maximum airflow, and that's really the reason for that design there. And then this skirt down here. So there's the back of the front cover, and the front of it. And the whole idea was that this perf was to go on, and this perf clips on the sides of the cover, and there's just one tab there that you bend over to hold it in place. Here's another, let's dress up something that's in a rack mount environment. What they were trying to do here is, this was the first box that basically converted internet to cable. In fact, there's gazillions of these all over the country. And basically, they got so you could start getting your internet through your cable system. But what they were trying to do is they were trying to put a lot of information into this panel, So they wanted to know where all these were, and they wanted it to get it in underneath, out of the way where it wouldn't wear off. So we molded, this is an undercut, and then they wanted the sides to be the handles, so we molded an undercut in over there. There's another better shot of it. And again, it all had to slide into a, a single rack mount bay, and it's the reason for the compact undercuts for the handles. This is an example of, this was a nice ID Magazine Award winner for us. We're happy about that. But this is an example of when designers don't talk to their manufacturing people. And we got the drawing for this. We were said, hey, here, make this. So we said, okay. It had a big undercut here. It had a big undercut here. And we ended up making it. We got it over there, and the guy says, they're breaking. And we said, what do you mean they're breaking? And he says, well, they're breaking. So I went over there. It turns out that they had this 35-pound cable that goes in the back side of this, and they hadn't told us about it. But they had a shape they wanted to make. This is, I'll just make the shape. So we said, oh, well, you didn't tell us it needed to have any structure. So we went back and developed some structure for them, and we had to put an insert in this that was machined out of several pieces and keyed together. They also had a deep undercut on the other end, and this is a clamp that held it down. But here's what we weren't told about. And in fact, this part probably would have been better if it had been a casting from day one, because of the structure needed here. But we were able to go in, because we have machining capabilities, we're able to go in and machine this, and there's a number of different key features that hold that together, so it can hold that 50-pound, 35-pound cord over and over and over again, being flexed up and down. And we never heard of the part ever failing. So we came up with a nice engineering solution. But that's, sometimes in thermoforming, people who have machining capabilities like we do can make a big difference in how your product comes out in the end. And it did get a lot of nice publicity in the end. The surgical laser had a few interesting things going for it too. They wanted these undercuts to hold the part together, and what they wanted to do is they wanted to have the top and the front be bolted down, because that was the working laser and the working gear. And what they wanted to do is be able to pop these side covers off pretty easily. So we developed a set of ball stud enclosures so that it would snap on underneath there, and then there was a quarter turn fastener at the end so that they would meet their FDA requirement for having a tool to take it off. Came out looking really clean. This unit here is a DNA sequencing unit, chip tester, molded in two pieces. This is a clear polycarbonate top. This is an ABS base. And one of the things is we molded this ABS base, and you can see the undercut here on both these sides, and then the part extends down. The reason for that was to get the part for fastening to go past the trim line and the opening line where it could be attached underneath and leave a nice, clean, presentable line here. And it was interesting, we were getting some static about the cost of the tooling, and they finally decided to go ahead, and then when they got it, they go, oh, we get it now. You were molding an undercut so you could, glue it from the back so nobody could see any of the seams. I said, well, what did you think I was going to do? Just trim it and glue it on the top? And he goes, well, that's what the prior vendor did. We thought, okay, well, maybe we had a better idea. On the ends, what we did is we again used retractable slides in the tool, and that gave us a nice uniform area on the ends, so the vents all look uniform, and you could put the perf behind them very cleanly. Again, very, very tall, difficult draw part, but came out very elegant. Telecom's an area that we've suddenly found a lot of interest in, and everything that you see here, except this, which is a casting, these are all thermoform parts. That's Cisco's 84 terabit router. That's the backbone router of the internet. And when they first came out with that, 84 terabits, I said, you guys got to put this in language I understand. They go, we can download the Library of Congress in 4.2 seconds. So that's how fast. These are the internet systems that really the YouTube and all that stuff that's eating up all that bandwidth. This is the reason for it. And they have the capability. This capability came out a few years ago, and we're going to look at this grill in particular, even though this polycarbonate door is pretty challenging as well. What they wanted in that grill is they had so many chips in there, they thought the thing was going to burn up, and they were trying to figure out how to get enough air through it. So we made this grill, which is very technologically difficult to form in the first place, but then they also wanted it to be an information center, and you can see all the LEDs on the part here. So this is what it looks like when it's molded, and you can see here's the LEDs, and there's like 30 LEDs in the unit. And here they are from the back. So Mr. Chambers looks pretty happy in this picture. His stock went up a lot when that router was released. This is a dental laser that we did a while back. This is a pretty interesting unit. This is not very attractive, and we did the industrial design on this, and this is what we came up with. And so you can see again, liberal use of undercuts to match up with lines. This was molded in color, and then the rest of the panel was painted because this is the bumper. So we paint that, we molded in this color, molded in the texture, and then the rest of that part is painted the color, and the bumper absorbs all the shocks. A little bit of a difference, wouldn't you say? And then this is one of the last major industrial design projects we were involved in. This is a ultrasound generator for St. Jude Medical heart ablation unit, and for these look like beauty grooves, but there's really ventilation slots hidden in there. We molded in a cord wrap back here. Here's a shot of that undercut on that. It's a 6-piece removable core to get that molded in, but definitely worth it as far as keeping that weight down on the machine and having a complete seamless product back there. And that's the final look of it. Thank you very much for your time. Again, we're in booth 1883 if you want to come by and see more parts and actually hold them. Are there any questions? Yes, please. There's a mic right behind you there.
What is the tooling made of?
Our tooling is temperature controlled aluminum. We don't use any wood, we don't use any epoxy, none of that stuff, because we're making really nice precise parts, and wood tools and epoxy tools will break down and you'll end up with garbage. Anything else? All right, I guess we're done. Thanks.